Imagine a place where the sun never sets, a realm of endless sunlight where day stretches on forever and shadows never fall. This is not a fantasy from a distant world, but a possibility that exists just beyond our reach, high above the clouds, just a few hundred miles above our heads. In the silent expanse of low Earth orbit, the sun's rays shine with relentless intensity, unbroken by weather or the turning of the Earth. For decades, this simple fact has inspired one of humanity's boldest and most imaginative ideas: space-based solar power. The dream: to capture the sun's energy where it is most abundant and use it to power our world below. The concept is elegant in its simplicity. Build vast solar collectors in orbit, free from clouds, rain, and the endless cycle of night and day that limits solar panels on Earth. These orbiting arrays would gather sunlight around the clock, then beam that energy down to Earth using powerful wireless transmission, like invisible bridges of power connecting space and ground. It promises limitless clean power, a vision straight out of science fiction, where cities glow with energy harvested from the stars, and pollution is a relic of the past. NASA, Japan, and Europe have all explored this dream, launching studies, prototypes, and ambitious plans to make it real. But each time, reality intervened. The cost of launching massive structures, the complexity of building and maintaining them in orbit, and the technical hurdles of safely transmitting energy back to Earth proved overwhelming. Now, with the rise of reusable rockets and renewed ambition, countries like China are making space solar power a national goal, investing billions and racing to be the first to turn this dream into reality. But has anything truly changed? Are we any closer to overcoming the barriers that have stopped us before? The laws of physics and economics remain as stubborn as ever, reminding us that every breakthrough comes with new challenges and costs. The story of space solar power is one of ambition meeting reality, a cosmic dream that keeps returning, refusing to fade away, no matter how many times it is set aside. We're drawn to the idea of capturing the sun's energy before it even reaches our atmosphere, harnessing a power source that is as old as our planet itself. We imagine it as the ultimate technological achievement, a symbol of human ingenuity and our ability to shape the future. This vision endures, pushing us to ask, can we finally make it real, or will it remain just out of reach? A dream that inspires but never materializes. The question lingers: is this the dawn of a new era, or simply another chapter in our long history of cosmic aspirations? The allure of endless sunlight continues to inspire, fueling our imagination and our determination to reach higher, to do more. Even as the obstacles remain immense, the dream of a world bathed in endless sunlight refuses to fade, lighting the way for future generations of explorers and innovators. The biggest obstacle to space solar power isn't just the technology, it's gravity itself, an invisible force that holds everything tightly to Earth. Escaping gravity's grip requires an immense amount of energy, and with it comes a staggering financial cost that overshadows every other challenge. Every single kilogram sent into orbit demands a tremendous amount of fuel and resources, which translates directly into astronomical expenses for every launch. To build a gigawatt-scale power station in space, we'd need to launch tens of thousands of tons of hardware, solar panels, support structures, electronics, and more, each piece adding to the cost. At today's launch prices, just getting the necessary materials to geosynchronous orbit could cost $50 billion or even more, and that's just for transportation. This figure doesn't even include the costs of assembling the station in orbit, developing new technologies to make it work, or constructing the massive ground stations needed to receive the power. Even though reusable rockets have made launches more efficient and slightly less expensive, the overall cost remains the single greatest barrier to making space solar power a reality. Private companies like SpaceX and Blue Origin have made impressive progress, driving innovation and lowering prices, but not nearly enough to make such enormous mega-projects truly affordable. The physics of spaceflight, balancing energy, mass, and cost, are relentless and unforgiving, leaving little room for shortcuts or easy solutions. Until we invent a radically cheaper way to reach orbit, like a space elevator or another revolutionary launch system, the economics of space solar power simply don't add up. The dream of harnessing the sun's energy from space is beautiful and inspiring, but for now, the price of defying gravity keeps it just out of reach. For the foreseeable future, the first step towards space solar power remains just too expensive for us to take. Reusable rockets, like those from SpaceX, sparked hope for affordable access to space. The dream: if rockets could be reused, launch costs would plummet, making space solar power possible. In reality, reusability has lowered costs, but not by orders of magnitude. Extra fuel, landing gear, and refurbishment all add complexity and expense. The savings are real, but incremental, not revolutionary. Even the most advanced rockets still cost thousands, not hundreds of dollars per kilogram. The physics of launching mass into orbit hasn't changed. For now, reusable rockets are a step forward, not the giant leap needed for space solar power. The economics remain daunting for projects requiring tens of thousands of tons in orbit. Hopes for ultra-cheap launch are still just that, hopes. The gap between dream and reality persists. Reusable rockets are progress, but not the breakthrough this megaproject needs. For space solar power to truly make sense, we'd need more than just a few satellites and astronauts. We'd need a thriving, self-sustaining industrial economy in orbit, buzzing with activity and innovation. Imagine factories, mining operations, and automated assembly lines already established in space, working around the clock to process raw materials and manufacture components without relying on constant shipments from Earth. Only with this infrastructure could we realistically build the massive structures required for space solar power, using materials sourced directly from asteroids or the moon, instead of launching every nut and bolt from Earth's deep gravity well. But here's the paradox. Advocates claim that space solar power itself will be the catalyst that creates this orbital economy, jump-starting industry, and opening new frontiers. Yet the harsh truth is that space solar power can't be profitable or even feasible until that industrial economy already exists to support it. It's a classic chicken and egg dilemma, where each side depends on the other to come first, creating a frustrating loop. Some visionaries propose using slow, solar-electric tugs to gradually move components to higher orbits, inching toward the goal piece by piece. But this approach adds years to construction timelines and introduces new technical risks, making the process even more daunting and expensive. The reality is simple. You can't start with the roof before you've built a solid foundation. Every great structure needs groundwork first. Today's space economy is built almost entirely on data, communications, navigation, and Earth observation, not on heavy industry or manufacturing. Until a truly profitable space industry emerges, capable of supporting large-scale construction and resource extraction, megaprojects like space solar power will remain stuck in a logical loop, unable to break free from their own requirements. The infrastructure must come first: factories, supply chains, and workers in orbit before the dream can become reality. Otherwise, the numbers never add up, and the business case falls apart before it even begins. For now, the dream of space solar power is trapped by its own paradox, circling endlessly, waiting for the breakthrough that will finally set it free. Suppose we overcome launch and construction. How do we get the energy down? The plan: convert electricity to microwaves or lasers and beam it to Earth. But safety demands the beam be spread over a huge area, making it far less intense than direct sunlight. The ground receiver, a rectenna, would need to cover tens or hundreds of square kilometers, creating a massive, restricted zone. Building and connecting this rectenna would cost billions more. If you have that much land, why not just build a solar farm? The ground solution is simpler, safer, and cheaper. Step back, and the case for space solar power collapses under a simple comparison. Space solar requires rockets, robotics, and vast infrastructure, costing hundreds of billions for a single gigawatt. Meanwhile, terrestrial solar farms with battery storage can deliver the same power for a fraction of the cost. Solar plus storage is already being built worldwide because it makes economic sense now. Space solar is a solution in search of a problem that's already been solved. The resources needed for one orbital station could revolutionize clean energy on Earth. For practical, affordable, clean power, the answer is right here on the ground. The smart money stays on Earth. Why does the dream persist? Human psychology and our love of mega projects. Massive projects are driven by optimism bias. We underestimate costs and overestimate rewards. Space solar power is the ultimate example. Every part is at the edge of our capabilities, yet the vision endures. Like the Apollo program or ancient cathedrals, it's less about profit and more about national ambition and technological prowess. Governments revive the idea not for energy, but for prestige and strategic advantage. Its true value may be symbolic, a modern cathedral in the sky. When China announces space solar plans, it's not just about energy. The project drives innovation in rockets, robotics, and power systems. Technologies vital for space dominance. It's a civilian justification for investing in capabilities with military and strategic value. This sparks a global race. Other nations respond, not for economics, but to avoid falling behind. The project becomes a contest of technological supremacy and national prestige. Success is measured in capabilities, not kilowatts. The public narrative is clean energy, but the real game is geopolitical power. The competition for the cosmos is underway. Harvesting the sun's energy in space is a breathtaking vision, one that stirs our deepest aspirations. But a beautiful dream is not a practical plan. The barriers, cost, physics, and infrastructure are immense. Even with reusable rockets, the economics don't work. Simpler, cheaper solutions are already here. Solar, wind, storage, and smarter grids. The billions needed for space solar could transform clean energy on Earth, making a real difference now. Yet, we shouldn't discard the dream entirely. Grand visions push us to innovate and inspire future generations. Let's keep dreaming of cathedrals in the sky, but build our clean energy future here, where it matters most. The cosmos can wait. Our planet cannot.